if Raoult's law holds, that is just equal to this ratio of vapor pressures. But it's a parameter we will revisit and define in a more general way fairly soon. But it makes it easier to write this out. So here's my equation, and now I'll solve that explicitly for the vapor pressure of component 1, and this is the equation on which we will iterate. So it's the basis for our iteration. Yeah?
Should that be alpha 2-1 there instead of alpha 2-2?
Did I write 2-2?
You have P over x1 plus x2, then
Oh, yeah. Thanks for catching that. I would never have seen that. There we go. And if I had written alpha 2-2 is trivially 0. If I had written alpha 1-2, then of course it would be the ratio of P1s over P2s. So this is going to be the basis of our iteration. Now, we have to get started with an iteration. What we're iterating on is temperature. We want to find out what the temperature is that finally solves this equation. So we start out with a guess. And one way to systematically get a guess is to just take the, and I'm calling the initial guess here T with this superscript 0 in the parentheses. I can just take the mole fraction average of the boiling temperatures of the two pure components. And that means inverting Antoine's equation here for component 1 and component 2. That gives me these values. And finally, it suggests a starting temperature of 89.1. Fact is the iteration converges very rapidly. So if you pick something way different than that, it would just take maybe another step or two to converge, but you'd still be okay. But this is kind of the systematic way to do it. Now the iteration proceeds as follows. It's convenient to calculate alpha 2-1, which we remember is the ratio of these two vapor pressures. Once I've got alpha 2-1, I can go up to this equation and calculate the vapor pressure. So that's step 2. And now that I've got a vapor pressure, I can invert the Antoine equation for component 1 and calculate a new temperature. Now that I've got a new temperature, I'll go back and do it all over again, calculate another new alpha, then a new PS, and around, iterating it to convergence. Now I'm going to go to the next page here, and I'm going to repeat these equations so you don't lose them. But now I'm going to write this out more explicitly. So the first step here, we calculate the alpha, which is the ratio of those two vapor pressures. Convenient to write it here first as log alpha, because we've got Antoine's equation that give us logs of these vapor pressures, so here's what we have. So I'm writing it in terms of the constants A, B, and C that we have in Antoine's equation. And then, so that you have it all here, I've stuck in all the relevant numbers. So I need to calculate that for my initial guess. My temperature, let's write that as my initial guess temperature. And it turns out when I plug in all the numbers for that with a temperature equal to 89.1, remember T calls for degrees centigrade in this particular form of Antoine's equation, I get minus 0.63261, giving me alpha itself 0.5312. So I'm done with that. The first step is to calculate alpha now for the given temperature that I fed in. Then I can calculate P1S from the equation on which I'm iterating. So I plug in and I get 124.72 kilopascals. Then in step 3, I invert the Antoine equation for component 1 and calculate the now a new temperature. I'll call that T with a superscript here, parentheses 1. And that's here just in terms of these constants out of the Antoine equation, and I get the next temperature here, 87.81. So I'm already pretty close. I mean, I didn't get very different from the initial guess, but now I can solve the problem finally, and I put this, you know how to do this, but I'll show you anyway. So I can set this up as a spreadsheet in an Excel using macros. So here's my initial temperature, my 81.1, and there's going to be the temperatures and alpha and vapor pressure. And so here's my macro explicitly here for alpha 2.1. And then here's my macro to calculate P1S, and here's the macro for calculating the new temperature by inverting Antoine's equation for component 1. So once I've got those all in, I just and hit the button, I get numbers, and I just pull the columns down and see how far I have to go before these numbers don't change anymore. So a nice cleaner looking way where I don't show you the macros explicitly looks like this. So what I can do is if I want to do a number of these, I can be systematic about it. I want to calculate a bubble temperature. Here's the conditions for the problem I want to solve. I can write down the A, B, C values for the components 1 and 2 systematically. I can calculate the boiling point temperature, so there's little macros hiding in here as well, and giving me the initial value. And here is the actual spreadsheet that I've got. So when I pull it down even further than I need to, because you can see these numbers are not changing anymore. It tells me that it's converging very rapidly. So it meant if instead of picking 89.104, I could have picked 100, and I would just probably take another step or two, and I'd have it converged. So what I get out of this finally is this final temperature, 87.85 degrees C. And then the remaining part is to calculate Y1, giving me the vapor composition. So that's X1, P1S. I've got P1S, there it is, 124.86. So I put that in and get 0.739, and then Y2 is 0.261, and the problem is solved. So any question about this procedure? I tried to really go slow and explicit. So we'll be set up to do more complicated problems when we get to them. Yeah?
So which part of this are you iterating? Are you just iterating Antoine's, or are you just iterating Antoine's equation, or are you going all the way back up to calculate alpha and going down?
No, I have to go all the way back up and calculate. As soon as I get a new temperature, I gotta go calculate a new alpha.
Okay.
And then a new P1S, then a new temperature, then a new alpha.
Right,
and
so you're
P1S.
able to calculate both P2S and P1S from Antoine's equation?
You can do it. You can do it if you wanted to, but we really don't need it. Oh yeah, you have to calculate that as well.
To get alpha.
But the way I've written it out here is a little bit more explicit than I showed you above with the macros. A little bit simpler, so I put it in explicitly here as log P1S, log P2S.
Okay.
And then out of those I get alphas and proceed on. So if you understand this is really, for this is a really simple problem, then you'll be in good shape when we get to more complicated problems where you absolutely, what you have to do is do it this way. So that's it. I got finished with plenty of extra time here. So anybody got any questions or discussion? Yeah.
Do you want to do a more complicated problem with this?
In good time. I've got one more simple one. The most complicated problems that we get of this type are where you need a dew point temperature. This temperature is a bubble point temperature. We should remind ourselves of that. Especially it's a problem when we're going to be solving problems where you have a non-ideal solution, so there are gammas. And the gammas depend on x's. And so where that's unknown, now you've got a second layer of unknowns, because you've got the gammas that depend on liquid composition, which is part of our unknown. And so you'll have a number of additional columns in your spreadsheet. But if you get this, then that's going to be pretty simple. So I want to do, yeah.
Oh, I was just gonna ask, how far do you think we can get in this homework set with what we know right now?
Oh, good question. I've got to see what that is. I gave them all away. Anybody got one? Does everybody get a problem set? I printed a few less this time because so many people don't show up. And after that announcement, I didn't know if they're going to be happy here today.
He prints them out. No, because he prints them out, but he doesn't even give us room to write them. So it's like, it's like what's the
You
word?
can certainly do number one.
When
You can do
something is
number two.
meaningless, but it's like symbolic. It's like symbolic or something. I don't know. It's,
One
you
or
know,
two
it's
so
like
far.
I love paper. Here you go. You can't use it. You know, it's uploaded into Canvas. Go ahead and just throw that away.
Literally.